Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon, everyone. My name is Kim Ricketts, and I manage the Visiting Speaker Series for Microsoft Research. Thanks for coming on this beautiful day. I'd like to introduce Ken Kahn, our speaker today, to you. He is here all the way from, did you come all the way from Oxford just for one day in Seattle?
No, I'm here for the month in Palo Alto, so
Okay.
I did come one day from California.
Yeah, and then you're going back down tonight. Ken has worked on this kind of a project in many ways for over 30 years. It's culminated in a website and a patented product that he has called ToonTalk, which is a state-of-the-art programming language video game for children. I'll let him explain it to you. But I think we're all quite fascinated on how we engage non-programmers, non-engineers in the dialogue of the kind of things that we create here at Research at Microsoft. So that's why we invited Ken here. I'm thrilled to have him here. We'll do a question and answer at the end. So Ken, come.
How much time should
I would say speak for about 30 minutes, and then we'll get to that.
Okay, great. Good. Well, thanks for coming. So let me show you what I was planning to talk about. So one of the ideas, so Kim just mentioned ToonTalk, and that's been sort of my main activity for quite a while. But in the last 2 or 3 years, it's kind of led to some 2 or 3 other projects that I want to talk about briefly. And the theme that ties it all together is that even though ToonTalk is designed such that even very young children can build programs from the bottom up, one of the things we kind of discovered is, especially through some research projects that we're building on ToonTalk, that's what the Playground and Web Labs is about, is that a lot of the actions happening one level above the raw code, where you're giving the children or the students pre-built pieces that are carefully designed to be easy to compose, easy to inspect or edit, and they're not. Well, I even have a little slide here, I suppose, to show it. So that I think of them as autonomous little processes that can be hierarchically composed, and not what people normally mean by components, things like modules or classes or procedures or something. And one of the things you'll see in a second is how often you could just stick them together without worrying at all about how they interface, but sometimes you do a bit more. So so those are the 4 systems I want to show, and it'll be kind of a quick thing. And then what I also want to, but I'm going to show them with the theme of how you could do this kind of, some people call it middle-out programming, where you're kind of composing things to go upward, and then you're maybe inspecting, customizing, editing a little bit to go downward from the middle. And but as I show these systems, I wanted to kind of make clear there are other sort of big ideas underlying these different systems I'll be showing. So ToonTalk, the original conception of it wasn't so much this higher level composing of components, but it was this idea of what I call concretizations, so that all the computational abstractions about conditionals or communications or processes or all that are given concrete, playful analogs of things like trucks and birds and houses and bombs and things. Another aspect of ToonTalk is you're programming very concretely with examples and then later saying how you want it to be more general. And the other thing that was that rather than have any kind of standard interface that one might have for a visual programming language, to get the interface to borrow heavily from the way games work. And Playground was this European research project, went for 3 years, in which we were working mostly with 6, 7, and 8-year-olds, trying to help them and give them tools to build their own computer games. And part of the additional idea under that one is the idea that the way in which they could, the children even across Sweden to England or something, could communicate was using these communication facilities within ToonTalk that enabled you not just to send messages, but to send running programs back and forth. And maybe I'll have give you a little sense of what that was like. And Web Labs followed up from Playground working with older children, 11 to 14-year-olds, and there the focus was much more on learning science and math, but via programming. So the children would be building models of a food web or of a bouncing balls or of a lunar lander kind of thing. Or they'd be exploring mathematics. And one of the things that was particularly kind of well suited for doing that was the fact that Toontalk uses one of these exact arithmetic packages so there's never any round off. You could have millions of digits of accuracy because it's using rational numbers underneath. So that was all the Toontalk related kinds of things. And then the BBC launched this big 5-year, $300 million project that unfortunately failed after 2 years or something. But originally it was called the Digital Curriculum Project, and then it was launched as something called JAM so that little kids could remember the name. And we were asked to kind of build some proof of concept things of how much further they could go with this website in which the slogan was create, learn, play or something. So I wanted to briefly show you some of those things, though again, maybe we'll see how time goes. And then I got involved part-time in another European project that's called Remath, and the part of it that I was involved in, we built this system called Mopix. And Mopix is yet another system of which you could build your programs by composing these pieces and so on. But the really unusual thing is that instead of a programming language underlying it, you just have algebraic equations. So it's particularly suited for say, high school algebra or high school physics or something. And then the latest thing that I've been working on most of these things have been at the London Knowledge Lab, which is part of the University of London, but I also have a part-time position at Oxford where I've been trying to take these same ideas and ask, well, what would they be at the university level? And have a system called the Behavior Composer, which hopefully I'll have time to show. And then we just got funded for a follow-up project that's called Modeling for All that takes the same ideas but adds Web 2.0 and some Second Life ideas or something to it.
Don't worry about time. We have the room for an hour.
Oh, okay, because I am kind of rushing.
Yeah, don't worry. And also there'll be questions.
All right, great.
Do you want us to wait and hold the questions till the end?
No, either way is fine. Okay. Yeah, it's fine. Okay, so maybe after all that, we should start some of the demos or something. So start with Toontalk. So there's lots of things to say about just this opening screen. I'm using Microsoft Agent here to sort of... It's very hard to give a demo while he keeps talking, so I'm going to send him away or something. But part of the idea was to really make a programming language that worked from very small children all the way up to university level students. And we actually have succeeded in the sense that there were various universities that have used it even for courses in concurrent algorithms. At the same time, I worked with this doctoral student in Portugal who was exploring what could preschoolers do with Toontalk. And but one of the issues is that if you're trying to reach small children, lots of stuff to read could become a big obstacle. So it's important to kind of integrate text-to-speech and agents and so on to help them. So when I first started Toontalk, I had this naive idea that you just build a programming system in which people could build programs, and then everything will be fine. And discovered pretty early on that you need to produce all sorts of surrounding material. Yeah?
Text-to-speech is easy. Text-to-speech doesn't bore you to tears. It's difficult. How does
Yes, right, yes. No, that's a good point. And the majority of the children do send the speaking characters away. One of the things that one solution for that in some contexts, like here I'll show you a little introductory tour of Toontalk. Maybe I should minimize this. Oh, it's coming up. And what what's going on here is we actually have voice actors. I don't remember if this is the UK or the US version I've installed here, but in the second one, yeah, this is the UK version.
I'm Pat, and I'll be happy to show you around. If I hold down the right mouse button, we fly up.
So that is much more interesting than the synthetic speech, but of course you can't, it's not as flexible. It has to be only for canned speech. And one of the things that in ToonTalk's going on is that there's the need to not only compose sentences and speak them, and then you do have the problem that that a lot of people don't like listening to it. But rather than let this demo continue, maybe I'll just. One of the things that's cute about this is that it isn't just a playback of a video. You're actually just playing back the system. And if I click on this button, now we kind of jump live into this context. Hopefully. What's going on? See, it says I'm waiting. It's waiting for something. Yeah. Should be. I don't know. Oh, here it comes. I was just being impatient. Back to ToonTalk. I was just being impatient. Sorry. Anyway, so here we are. I'm just taking over. Oh boy. Oh, somehow we lost the audio though. Maybe I'll restart it. Sorry, I don't know what's going on. All right, we'll jump into free play. And in free play, so I'll say, I don't know, MSR, is that what it's called?
IMR.
Can't tie MSR. Anyways, maybe it'll look like this. Okay, so here we are. So the idea is that we're in this very plain, empty city, nothing going on in this their island, and the island itself is very impoverished. But when you go out, you're followed by this toolbox. If you walk into a house, it used to be that Marty would just greet you and start talking to you. And again, a lot of people didn't like him talking to you, so now he kind of indicates that if you push F1, he'll come in and help you and say things.
Marty here. I'll stay around to help you. If I bother you, just push the F1 button and I'll go. If I'm gone, then F1 will call me back.
So most kids push F1 at this point and just get rid of it. But some of them really, and one of the lessons behind that is that there really isn't a one-size-fits-all, that some kids really do like to have Marty around helping, some of them don't, some of them like to have him talking, some of them will want to jump into this puzzle tutorial game that I probably don't have time to show you. Some of them will want to sit there and watch the demos. There's a lot of different ways of interacting with the system. So when you sit down, you have all the building blocks of your programs here in the toolbox, and you have some tools you could use, and you have a notebook of various things. So maybe I'll show you really quickly this a very simple, quick example, but then I want to jump up to the level at which most of the children in Playground were interacting with the system, which I'll show you that in a second. So one of the first simple examples that's, and again, I'm really kind of rushing this because I want to cover so many other things, is suppose we want to have a robot that'll just keep doubling a number. So first off, the way we double numbers is you pick up the magic wand, make a copy, and then if you drop a number on a number, bam, the mouse smashes them together like this. And we could keep doing this over and over again. But wouldn't it be nice to have a robot do it for us, because they like doing repetitive things. So when I give a box to a robot, we enter into his imagination. Marty's here to help us if we didn't know what was going on, offering to help us. And all we want to do is have, now instead of controlling the arm, we're controlling the robot, but it's the exact same kind of actions. You know what, I'm going to have a mouse pad here, because somehow when I move the mouse, it's not always moving. So, so if we pick up the wand, copy this and drop it, just like we were doing kind of in the free play environment in the world indicate that we're done training. Then we've taught the robot how to copy the number 4 and drop it on top to make 8. But obviously that's a pretty limited program. So he does that, and then he looks at the box again, and it's a box with an 8, and he only knows how to deal with 4. But we know that it doesn't matter what number is in there. So what we could do is use this tool and make this program much more general. Now we're saying if the robot's thinking about a box with any number in it, then he'll do what he was trained to do. And then once he's done doing what he was trained to do, he looks at the box again and says, does it still match? So you implicitly have iteration, and obviously if you set things up so that it stops matching at some point, you could have it terminate or something. And there's one of the tools called Pumpy. All these have funny names, Dusty and Pumpy and Bammer. This will make things change the size of things so you could sort of see better what's happening or something. If I stand up, the robot will keep working on the floor even a little bit faster or something. But if I just walk outside even for a second and come back, then it's about to warn us. Maybe I'll just ignore this for right now. It's warning us that because our numbers have gotten so big, don't be worried if things take a little bit of time or something. And what's happened is that it was able to double this number, huge number of times in that brief moment we were outside. So let's stop the robot here or something. So here we have this number, and if we wanted to get a sense of what this number is, we could kind of move it around, and it just keeps going and going and going. So one idea that's we've explored a bit in the Weblabs project with just this idea of numbers, just integers, was if you take it outside and set it down in the grass, and then if you stand up, you could see the number's right there. Now we could go for a walk and see how big our number is or something. And keep walking and walking, and you get kind of tired, so we'll call for the helicopter, and now we'll go fly. And well, we didn't actually make it big enough, as big as the city. It seems as if we got one that's almost a mile long or something. But if we had let it run for a couple more seconds, I could assure you it would have been sticking out into the water, been a very big number. And one of the things that's kind of fun is you could, besides numbers, there's these other data types like text and things for communication, for comparison, for starting new processes. And then a notebook with all sorts of gadgets in it. And one of the things in here is a text-to-speech gadget. There it is. And if first off, you could just have it speak it.
Text-to-speech.
And I could type to it, say, text to what? I don't know, whatever. You could have it.
Text what?
Whatever. But if we erase it, then what we're saying is we want to convert whatever we drop onto it into a text-to-speech thing. So we take this number, and here we've converted it into
2 quinceptuagint 3,374 quartseptuagint 3,362 triseptuagint 3,775 duoseptuagint 3,000.
And it could go on for a very long time. As a matter of fact, one of the things for getting a sense of what big numbers are all about is to ask the question, well, how long would it take to say that whole number? And what you could do is copy and paste it into a text buffer and see that it's how long it is, and then just see how long it takes how far you get through it in 60 seconds. And one number we were working with worked out to 3 weeks before it would finish saying the number or something. So you can make very big numbers. You could also make very small numbers. We could take 1 and divide it by this number. So now we're going to have 1 over that ridiculously big thing. But of course, it's going to be an awful lot of zeros. As a matter of fact, if we fly to the other end, we ought to see something different, but it should be zeros for quite a long time. No, it's still zeros. Well, we'd have to go even further, and probably not the time to do it. So this is sort of a quick sample of kind of what it's like at the bottom-up level. But what I wanted to talk about more was about the component level. And so one of the things that they did in the Playground project, this was the project to help 6 to 8-year-olds build games.
Hi, I'm Kitty.
We could be bald this time. Is they built this city within Toontalk where there'll be areas where there's all sorts of components for building games. There's areas where there's clip art or clip sound effects, or and there's also areas where there's a lot of pre-built games. And what I wanted to show was give you a sense of what some 7-year-olds kind of did. So here's these neighborhoods. This is where you've got gadgets for moving or changing appearance or making sounds or reacting to events. And here you've got clip art, clip sounds. And here there's a lot of built games, pre-built games. So here we have a little Pong game, and I just grab a copy of it and set it down somewhere. And I could just play it. I could hide my hand or something, and can move the other one. Should be sounded. And I can make it a little bit bigger so we see it better or something. So that's okay, but you know, a game like that these days, you know, about a minute and you're tired of it. But the interesting thing is that it's completely malleable. So for example, I could take the magic wand and copy a ball and start it up again. Now I have 2 balls in my game, and they bounce off each other and everything. If I was curious about how everything worked, then I could say take one of these, take it off or take a copy, doesn't really matter, and then I could flip it over. And here's where the components kind of come in. I'm going to use Pumpy to make this bigger or something. So there's 3 behaviors, and each one is composed out of smaller ones. So here's one behavior that we could look at. Make this bigger or something. So this is the behavior that just gives it an initial movement horizontally and vertically, and the 2 are being composed. And at the bottom of all this, you finally get down to a box that's being given to a robot. And any of these things could be kind of explored on their own. If you want to see what moving to the right does on its own, I could just take it off, flip it over, even has a kind of a nice appearance, turn it on, and sure enough it goes to the right or something. And this one, if I put it back together again, flip it over, it'll move it. But here's the important stop there. The thing is that these things can be combined. I could take the moving upward behavior, drop it on this thing. And I could take the moving to the right behavior, drop it here, take this object, whatever it is, just a square, and when I turn it on, sure enough it does both. So you could not only kind of compose things at this level. So let me tell you two stories. And I'll tell you one story and then show you the other one. One story is 2 7-year-old girls in London. They started taking this game and they started initially just fiddling with the background color. And when it was blue, one of them said, "Oh, it's water. Why don't we have a game about fish?" So one of them looked around in here and found some, maybe I'll give you the first part of the story. So they found some picture of a fish in a notebook. And they just flipped the fish over. It doesn't have any behavior, it's just artwork. But that you could, let's get down here where our game is or something. we could take off one of these balls, spit it out, flip it over, and all those behaviors, you don't even at this point even care about what they're doing, about bouncing and starting to move and so on, and just give them all to the fish. So now when I drop the fish onto this, maybe I'll clean up a little bit. Now when I turn it on, we've got a bouncing fish. So they ended up adding, they thought the fish was lonely, and they added like 5 or 10 fish all bouncing around, and they thought it was silly that the fish were bouncing off paddles, so they changed the paddle into a shark. And then they said, but wait a minute, the fish shouldn't be bouncing off a shark, the shark should actually eat it. So then they had to go really down into programming to change that behavior. So that's one kind of story from Playground of 2 7-year-old girls in England. But the story I wanted to show you in a bit more detail is these 2 7-year-old boys in Sweden, and they had taken the Pong game, and they'd also played this real simple little Space Invaders game. I'm going to make it bigger. So you're this, maybe I'll move my hand. You could shoot anyways, or I could lose or something. And they had this idea, they were going to make space Pong. So what they did was they took the Pong game, probably made it a bit bigger, and the first thing they did was said, well, let's just copy the invaders into the Pong game. So they picked up the magic wand, copied this, and copied this somewhere, and maybe even 2 of them or something. And maybe the 3rd invader too or something. So now if we play this, we have our bouncing ball, and it bounces off the invaders, and there's all these funny sounds and stuff. But it's not, they realized that they wanted something more that had both Space Invaders and Pong combined. So what they did was they removed the ship from the Space Invaders game, flipped it over, and there's all these behaviors here, and they actually spent a lot of time seeing what each one did and playing with them and stuff. But we're going to be quicker than that, because all I want to do is find the one that'll shoot. There's even ones for joysticks and mouse, but I think this one says I fire in 4 directions, and they only wanted to fire in 1 direction, and this one's probably the right one. I fire white bow upwards when you press the up arrow key. Okay, so what they did was they removed the paddle. What? Oh, I got the wrong one. No. Oh, yeah, I got the fish game. Thank you. Somewhere I could stand up, maybe. Maybe I will have to stand up. I don't know. Oh, there it is. Thank you. Okay, so what they did was they removed the paddle, flipped it over. It's got these behaviors for being a paddle, and then they just combined with it just this one behavior of shooting vertically, and added this to their game. And then they could not only get my hand here, not only play the game, but it could shoot, and the bullets would actually blow up invaders. It wouldn't blow up the. I don't think it blows up the. Anyways, you could play. Maybe you get the idea that you could combine the behaviors of these games at this level of components, rather than having to always dig down to the level of robots and boxes and birds and so on. So maybe I'll show you some other examples of things. there's, of course, a lot more you could do with ToonTalk. One thing I should say maybe before we leave ToonTalk here is that you could grab this, hit a pause button, and you could turn it into a Java applet, add it to the project website, all sorts of things. So they made it very easy for kids not just to create these things, but especially in the Web Labs project, to share them and then have the objects right there in the discussion page or in the email for the other kids to maybe try out and comment on or improve or something. Actually, one more last thing before I forget. Because I mentioned another idea that was behind the Playground project was the way in which that you do communication. So there's this communication mechanism within ToonTalk that's based on the idea of kind of the metaphor of like homing pigeons. So if I give a bird anything, like this word pictures, she picks it up, takes it to her nest, and comes back. But I could actually take this bird, put it on the clipboard, paste it into a message, send it to Sweden. Some kid there could copy and paste the bird into ToonTalk. And then, if they had this game that they really liked, they could give it to the bird, and it'll just appear in London at the kid's nest. So that was a way in which they could exchange things in a way that was fit very well the sort of world they already knew, never had to leave the world in order to exchange. It's underneath this word pictures. And of course they could also say, you know, I just hit the wrong button. Hit the pause button. You know, what do you think about, you know, my game or something? And give that to the bird, and then it'll fly off to the other country, and so that they could have conversations this way. And I was even working with a bunch of 10-year-olds in England who I've been working with 4 of them, and they really knew ToonTalk well, but the rest of the class never got a chance. So we had a one day where the 4 kids were going to show the other kids what you could do in ToonTalk. And what they did was they got all the computers they made a very complicated communication network with lots of birds and nests, and started broadcasting and sending messages all around. And they really were able to sort of rewire the whole thing, because one of the things that's going on here is this is all sort of kind of first-class objects. That if I'm a kid in Sweden and I suddenly have a nest that I want some kid to be able to send messages to, I could put the bird or a copy of the bird into a box and send that to the other kid. So now that other kid now has a way to communicate back with me. You have a way to kind of rewire your whole communication structure. And what was fun was to see 10 or 12 10-year-olds just going wild with this thing. And of course then they started sending messages like, you know, somebody's got bad breath or you stink or something, you know. But it was interesting the way they were mastering the communication primitives here and able to set up a network. Okay, so let me move on to there's a really interesting idea inside of this one. Unfortunately, it takes a minute to load. So this was done in the context of this BBC project. So this is meant to be kind of very interdisciplinary, very educational, but very web-oriented. So it might be used in schools, but it might be just some kid at home who comes across this website. And this was not the polished kind of production value stuff that they had on their website. Those, you know, cost many millions of pounds. This is proof of concept kind of software. But the big new idea in it, okay, so let me show you this, is, well, this was just meant to be the screen that you might run across that would encourage you to go further. Here's what you might be able to do: build a lunar lander game or this astronaut game, and it'll be fun, but it'll be kind of hard, but you'll have people help, you'll have virtual characters helping you and so on. So because this was just done as proof of concept, we didn't have an artist, but we had 2 of the kids in the project volunteered to make all the artwork. So you could click Kid 1's artwork or Kid 2's artwork or something. But the important big idea here is that this was a vision of a game for making games. So it's a game in which the player, as it says right here, it's your first day at the game development company, and you're in charge of building some games. So here's the director of the company telling you, well, let's start with a really simple game of just an astronaut in space and has to get back to the ship, and don't worry if you don't know how to do anything, because I've assigned a whole team to help you or something. So here's the team. So you have the programmer who, if you go to her right now, I think she'll say, great idea, but I don't know what to do, because but you better find, you're going to have to talk to others about what to do. So we could go back. If we go to the scientist will maybe say, got some ideas, but maybe you're going to have to go to the game designer, the assistant game designer, to get some ideas as to how this is going to fit inside of a game. And you go back and forth like this, collecting various suggestions, ideas, but also eventually kind of resources. So eventually the programmer will give you some equations. Then you can go back to the programmer. The programmer says, okay, great, I understood that. Here's some code. And so the other thing was, the idea, if you can make this sort of a playful game, is not just to have sort of stick to the task, but to kind of have characters with little different senses of humor or different So one guy is always spitting out poetry, which I just sort of Googled for space poetry or something. And it turns out some famous poets did write some poems about traveling in space. But here was just a cute thing, which was the fact that England's first astronaut was from Mars, because her job was at the Mars chocolate factory and so. And if you clicked on this and we had the internet connection, you'd actually go to the BBC history page and learn more about her if you're interested. So the whole idea of this should be a good experience, even if you got 5 minutes. But if you got a few hours, you could really go kind of deep. And there's more, but again, I wanted to give you a sense. So if we say, let's make the game, we haven't really gone through the metagame far enough that we've really got the resources or know what we're doing. But as part of the demo, I'm going to say, I want to go ahead anyways. And unfortunately, good enough for this demo. Normally, when you start up this thing, you could either go straight into the game making, then you get the full-fledged game making thing with all sorts of features. Or if you started going through the game, then you get this kind of a very simple kind of few building blocks, and you have to go back and talk to more people and get a few more things, get it back. So I think we're in the mode where there's just a couple gadgets. But maybe I'll still give you a sense of what. So this isn't built on Toontown, it's actually built on a version of Logo. And this is analogous to those Anima gadgets that we saw in Playground. I don't know if I called them Anima gadgets then. So, so this one is sitting there built out of this one piece of code. Here's a bunch of comments. Here's the code. The red parts are parts that you should feel free to change even if you don't know what you're doing. And the other things you should probably know what you're doing or something. But you don't have to go this deep. So one of the concepts underlying this is what we call layered learning, so that you could go very far without ever looking at a bit of code, but if you wanted to kind of have more control or kind of learn about the programming, you could do it. But once you have a gadget like this, you could just drop it on something like this, and now it's got the ability to move horizontally or something. And maybe we'll give it an initial velocity. So now it's got these two behaviors on the back. So now if I say start the game, there it goes. Not a very exciting game yet, but eventually there's quite a lot of good physics going on in here in terms of conservation of momentum and Newton's laws and all these kinds of things. And there's even a version, the button, but where you could have a two-player version. So you could play where another kid could be on another computer on the same network, could be playing the game. And what's funny is that in this case, the whole concept of the game was this sort of rescue thing, where one player could be controlling the lunar lander and the other one the astronaut, and you're both trying to, the astronaut's trying to get back, and the pilot and the lander's trying to rescue and it's a cooperative game, and it was all fine, tested. And then of course the first time we tried it out with some 13-year-olds, they decided that that's the wrong game design. They built their game so that the astronaut's trying to get back and the pilot's trying to get away from them to just leave them behind. Yes, so they had a very different concept of what the game should be. And one of the cute things too is when you switched from this game to the lunar lander kind of game, that many of the same building blocks applied, that you could sort of see the commonality of the physical processes and computational processes. And also for any of these objects, if you flip them over, you could get help from any of those 6 different characters about that object, either about the behavior or the object, or you could click on settings, so that the idea was that you could, like, what does it say? I don't know, change the mass of the lander. So here you could, just get a slider for just making this change. So you didn't have to even touch the code as in the previous things, but you had this little slider. And then you could even kind of use this. Well, it seems strange. I guess it was NASA had a heavier, I don't know the numbers. But you could even have the historically accurate one. So this was another experiment that's building on the same idea of this sort of middle-out programming, where you're not expecting them to learn logo programming and what variables or conditionals or procedures are all about. Instead, they're kind of grabbing these gadgets and composing them and parameterizing them, and also adding other things to their user interface, various kinds of graphs and so on. So let me move on. I think it's probably best. Okay, so Mopix is still, all of these ones I'm talking about are kind of past tense, but Mopix is like the middle of this project. And this time it's implemented in Flash, which is very nice in the sense that you could go to the website and just play it without having to install anything, which is getting to be increasingly important in schools, at least in the UK, that even teachers aren't really allowed to install things on the school computers without a huge lengthy bureaucratic process. So what we have here is just like before, you kind of pull out an object and the object doesn't have any behaviors on it, doesn't have any properties, but we could sort of take, instead of dropping little bits of code on it, we're going to drop little bits of equations on it. So here's an equation that sets the initial the horizontal velocity, and we just give it to the thing. And here's one that actually defines what it means to be, I wonder what I could do about, there's probably some zoom thing, yeah. No, zoom in, right, yeah. Here we go. So the me here is just the object that you're going to attach this to. So when you drop it on, it's going to become object 1 or something instead of me everywhere. And it's just saying that the x position at some time is just its previous x position plus its velocity at the current time. Let's get back to this. So we could keep adding more and more equations to our objects. Here's one for acceleration. Here's defining velocity. We could even have things, predicates that we add to it for like bouncing or something. So now we should have something that moves to the wall and then should bounce off it when it gets there or something. But the important thing is that this becomes a tool for not just sort of computational things, but also for learning about algebra or physics. And just to kind of give you, if I had a web connection, I could be able to go to the website where you could save and restore models. But actually I have, I think, well, I'll find it. I have a model that I think I'll find it pretty quickly. So again, this is only because I don't have a web connection. So here's the representation of this model in MathML, which is a kind of XML. And if I go back to our tool here and I say XML, this is the XML of what we just built. But if I replace it by the new thing, something happened here. What happened? I saw it come and go. Here we go. So this was something one of the students built. They just had two balls that bounce, and then the black square was defined to always be at the average position of the two balls, and also to leave behind this kind of colorful trail. And she was doing this kind of just playfully, but it's pretty interesting from the point of view of kind of math education, because there's a lot of things that are interesting, like why does it kind of go vertical up and down for a while? Here it's going to go do it again, and other times it's moving horizontally. What's going on there? And it's interesting to kind of have students play with this and try to figure it out. Generally, most of them figure out that if the two balls are moving apart at the same speed, then the average is going to be no motion, and that's why it's moving vertically. So when both balls are moving left or both moving right, then the square moves left or right. But otherwise, if they're moving in opposite directions, it just moves vertically. So that one is developing. We're in the process of building a sort of more of a web-based AJAX kind of version of this, so that it's even more featureful and flexible and stuff. But again, the really surprising thing is how far you could get with just equations and not any kind of imperative programming there. And there is also a whole editor here for building equations, but I don't really have time to show that or something, whatever. Okay. Almost done with demos. So here's yet another version of the same idea of kind of providing these chunks of code that are easy to compose, but this time it's at the level of university students, and it turns out even researchers have been interested in this. And there's a couple new ideas in this one as well. So one of the new ideas that's really worked out quite well is this whole bottom area here is an ordinary browser, and this whole thing is sort of a Java application that helps you put together these programs and then runs them with yet another tool. And if we say that we want to browse for behaviors, there's all sorts of behaviors that are sitting there on this website, which happens to be a wiki. And there's ones for movement and appearance and reproduction, eating. And there's also a whole bunch of them for that are reconstructions in a very modular way of models that have been published, and often by people that we're working with at Oxford. So maybe I'll show you the basic idea first, and then I'll show you sort of a neat model in a second. So if I click on Move Forward, on this web page here, we have a little summary of what it does, the code itself sitting here, a button that if we click it will add it to an object. In this case, we didn't give it a name, so it's just called Prototype 1, a description of how you can make variants of it, related behaviors. But even with this simple model of just two objects, one of which has a behavior, the other one doesn't, I could say run it, and what's constructing, in this case very trivially, putting that one thing together into a program to run in this other tool that's from Northwestern University, that's a very popular modeling tool for both beginners and for people in other fields. So here we see the object Prototype 1 moving forward, this one not moving at all. So again, just like with you saw even with the ToonTalk one, you could start combining these things. So like a related behavior is one that'll turn randomly a little bit to the left or right. So if we add this to the prototype and we say run my model, and I click go, now we see it's kind of moving like this. And it's trying to keep a constant speed. If I do this, it'll just run as fast as it can or something. But if you try to make a simulation, you often want everything to have a constant relationship between simulation time and real time. So let me show you a more serious model here. So if I go back to the browse, I'll show you the vaccination one. So we're working with this professor of mathematical biology at Oxford who's written papers of modeling diseases and vaccine policies and stuff, and we kind of took it and mapped it into, hopefully it'll find it. Yeah. Maybe there's this question of whether there should be a local copy of it, but maybe it doesn't. I don't know what's happening. Because the problem again is that I don't have an internet connection, so it's trying to use this local cache. Doesn't seem to be finding it. But I'll show you another model that's interesting that I know is sitting here on this machine. Sorry. Where's oh well. What's going on? So here, this is one that we've worked with the business school at Oxford. So we've had MBAs and some other master's students who are never in their lives going to need to build computer models, but the professor involved understood the value of what he called modeling literacy, that the idea that students should at least have some understanding of what limitations, the possibilities of modeling, because they're going to be probably interacting with people and relying on computer models. So here's one that's based on this book called Growing Artificial Societies. And you could see there's quite a lot of behaviors that have been added to each agent and the environment and some other ones. And if I just click on Run My Model, we could see how it runs. So here we've got a bunch of agents all starting off in the corner here. And the yellower areas are where there's more food or resources. And some of them have different abilities in terms of how far they could see or how much energy they consume or money they consume. And then here we're actually doing this thing that's kind of called a Lorenz curve, which is just showing the way in which wealth is distributed in this community or this society. So the straight line would be if everybody had equal amount of wealth. And you could see that as this is evolving, there gets to be more and more inequalities just by the very kind of basic nature of this society or something. And it's also producing various graphs and stuff down here. So they could explore kind of different models. And also what was very good pedagogically was that we had them build this model in like 15 or 16 smaller steps. So they would take a step and just run it, even though it was just one object moving around a really simple world. Then they would add another step where the world would have a little bit more, and then they'd have more objects, and then they'd introduce life and death or various kinds of things. So each time they would kind of get a sense more of what was going on because they were building it in a step-by-step process. And we have other ones working with in zoology with schooling fish. I mentioned the epidemic one. There's, I don't know, a few more of these kinds of models that we're doing. And then I mentioned that where we're going next is this new project that's going to try to create a website in which it's much easier for everybody to build these kinds of tools, but also to share the models, the micro behaviors, also be able to tag and rate each other's work, discuss them, sort of all the advantages you get from kind of a social online network like that. but in this case, instead of being like for Flickr for photos, it's our software for computer modeling. And then we had the idea that these same microbehaviors could be implemented both in our system and also in Second Life, such that you build a model of how fish school, and then you could import it into Second Life and experience it kind of firsthand by seeing the fish, not only first-person point of view, but you could even be a fish or ride a fish and see what it'd be like and see how much you could influence it. So I think at the end here, so. Yeah, I hope so.
I have one.
Okay.
In terms of studying how people interact, clearly a large part of it is watching what people do and tracking that information.
Mm-hmm.
Is that one of the big components of the creation of it, or is it just kind of grown out?
So there's a couple dimensions. One is the sort of the one that's sort of informs the software design, and the other one is all the research in terms of what are people actually learning from it. So one point of view is that it doesn't much matter. This is just a tool for being creative and expressing yourself, and we all are pretty sure they're learning great stuff, but we don't have to kind of demonstrate that. Or the other thing is to show, that as a result of using the software, the children understand Newton's laws better than some other group or something. So for the latter question, like within the Weblabs project, different partners had very different approaches. So like in Cyprus, they really did take this approach of pre-tests and post-tests and getting over 100 students and careful measurements of what was going on. While in Sweden and in England, they were much more of, carefully analyzing a 10-minute little video segment of what two kids were doing and kind of looking at it in fine detail, and then drawing conclusions about how much they must have understood in order to be able to do this or say this, or how they were using the software to refer to concepts that are normally very abstract, but they could just point to them in this case or something. And then in terms of the software, it really has been more of this sort of informal process of having all different kinds of testers, all different kinds of ages, and getting lots of different kinds of feedback from them, both sometimes verbally, sometimes watching them use it, sometimes, when I showed that little demo in the replay of a demo, like the introductory tour, that's something very easy for users to create. So sometimes you could replay what a user was doing and see where some kinds of confusion was happening or what. But it hasn't been sort of a real formal process. It's very important, this sort of iterative design, kind of getting things back from users. And one thing I should say on that related topic is it's very tricky, this issue, the extent to which kids are really co-designers, because that's one of the common slogans. But when I early on was working with kids, many of their suggestions were kind of missing the big point. They would, they would go on and on about how, you should be able to walk into the water and then there should be sharks and you have to avoid the sharks. And that'd be kind of a fun thing, but it'd be kind of peripheral to the whole point of what Toon Talk's really about or something. On the other hand, there were kind of computer science-y reasons why certain things you couldn't put into a box. You couldn't put bombs into boxes for reasons that I could explain from a computer science point of view. But when the kids would try to do it and say, why can't I put a bomb in a box? I could put, birds, I could put numbers into boxes, I could put boxes into boxes. And when I realized I couldn't give them an explanation at their level, I started realizing, well, maybe, they're right, and the computer science kind of issue was kind of not really. So that wasn't a case where the kids I think were right that it should have been more uniform, even if there was a story from computer science as to that a bomb is really more of expressing an action. Well, it's not really an object in the sense that the other things are. So it was a different category, and it shouldn't be in a. But that wasn't the kind of way the kids wanted to think about it. I think they were.
I think there's a value to accumulating the way that people, that don't normally don't come to the computer science world, how they interact and kind of ideas they have and their questions and how they move, and there's a huge value to that.
Yeah.
Aside from whether or not the kids get smarter or they actually make an interesting game, just them interacting should be huge.
Right. No, you're right. And actually, before you do that question, no, I was going to show you something, but I think I need the internet connection. But there was, in WebLabs, we really were encouraging the kids to interact around their ToonTalk programs, and there was a really nice example of that that I have the link for, but again I don't have the connection, where this girl in Portugal had made a robot that made this kind of complex sequence of numbers, and she posted the first few numbers as a challenge to other kids in the project. Could you figure out what my robot was? And this two kids in Bulgaria picked it up, and they came up with completely different robots than hers, and then that led to this really interesting discussion between these three kids about, well, how come our robots are doing completely different things but they're producing the same numbers, and will they always produce the same numbers, or is it just the first ones that they're seeing? And it really led to a lot of nice back and forth. And then one of the kids in Bulgaria said, well, my robot with these other inputs will produce this sequence, could your robot produce it? And there was a lot of back and forth that was quite interesting and valuable, and an indication these kids were really kind of excited about what they were doing, and the fact that they were not just building these programs, but that they were in the social context of kind of sharing and challenging each other was really important. On the other hand,
How did that work? The physical metaphors, the mathematical metaphors, they cross languages, they cross cultures, but how does communication between the kid in Bulgaria and...
Yeah. Well, so I think it helped a lot, the fact that the ToonTalk programs themselves were just robots that were picking up numbers, doing multiplications, additions. There wasn't even the issue of trying to understand somebody else's program where the variable names are in another language or the procedure names. And then in terms of what they were saying on the web's discussions, I think the Bulgarian kids actually did have an adult help them with the English. So they kind of had some adult explaining in Bulgarian what the Portuguese girl, actually, her English was quite good. I mean, she made a bunch of mistakes, but it was still quite clear what she was saying. Actually, you guys could probably look at it, and I can't. Let's see. I think... I don't know. See... let's see. It's probably not worth doing this, but because this is the ridiculously long URL. Never mind. But wait, it's in my cache a little bit, it seems, even though I'm not connected. Yeah. Because I looked at it the other day, so it's still good. Anyways, so she says, I created this sequence of numbers. My first terms of the sequence are, and then she didn't have the solution here later. She edited this later after a lot of discussion and stuff. And then this kid Nasco he said, well, here's my solution, and if you look, her robot was working with 3 different variables, 2, and times 4, whatever. This one was working with I don't know. They really are quite different. And then he posted back, And these things are things which, if you click on them, well, normally you would be able to download it into ToonTalk and it'd become live, real in ToonTalk. So you would see the little message, the box that this robot would work on, and just could try it out and go back and forth. So this was a very nice thread, but to be honest, there wasn't too many. Oh, and this kid was really proud of the fact that he had a robot that was reusing, so he had fewer variables to produce the same sequence, and he said he could, only have 2 holes in the.
When you're saying kids, what age group are you talking about?
Yeah, so Rita I think was 14, and I think Nasko and Ivan were 10 or 11. But the Bulgarian kids were the Portuguese kids were in an ordinary school. The Bulgarian kids were, I think, in a kind of after-school math club or something. So they were very math-oriented, but they were younger.
Did you ever find any lower limits on an age group that used or had problems using this?
No, that was the really nice, pleasant surprise was that even this research that Leonel Morgado was doing in Portugal with 4-year-olds showed that they were really able to understand about robots and about birds and able to build little programs and play with them and seem to have an understanding of what they did. The disappointing thing, so that was the really exciting thing, was that even very young kids were understanding the computation model. But the disappointing thing was how they really couldn't be very task focused, or they didn't know how to really use what they did to accomplish something. So they understood the basic building blocks, but if they had a little goal, they didn't know how to assemble the building blocks to reach their goal. So it was all very kind of tinkering around and never trying to solve a problem or do any planning. The younger kids especially.
Well, there's obviously a huge body of work here. I'm interested, is there a place I can go look for a taxonomy of types of composition or data about what sort of compositions are intelligible and what sorts aren't?
No, I've been wondering about that too, because there's been this theme, as I said, running across much of all these projects about composing things at this level, and yet I haven't found, or people haven't pointed me to, literature at this level. Of course, it's very hard to find because there is a lot of stuff about modular programming, component, but in this kind of sense in which they really are more like concurrent processes that you're adding, and that they're really well designed to fit together. So maybe I should try to write a paper like that myself or something.
Because we know a lot about how to program, how to compose, even if we think like a programmer. Thinking how to compose when you're not thinking like a programmer is something that doesn't seem
right.
well understood
Yes.
at this point. I was wondering if there's work, prior art I can go look at to get my head around that.
Now, one of the things, I was just this morning with the Popfly group here, and they're very much kind of dealing with some of these same issues, and also the work on Boku. As a matter of fact, there's I mentioned, I think the Playground project was building both on Toontalk, and the other half of the project was building on Logo, and they built something that was kind of a simpler 2D kind of analog to this work on Boku that's going on here and stuff. So there is some nice connections, and I guess I should be making clear too. I kind of took examples from my own work, but there's the work from Berkeley and Andy DeSessa's group. There's Alan Kay and the Squeak project. There's MIT now with Scratch, and before that various logos, and then I'm building on the Northwestern work. So there is 5 or 6 places in the world that are kind of trying to do something like this, but they still, like Toontalk without the additional layers, are kind of still having this bottom-up kind of style. Yeah?
Technical question. When you compose behaviors, they may interfere. So, for example,
right.
If I have something that moves to the right and something that sets it to 0, is there some error checking going on? When
No. Yeah. So in the Playground project, this did come up because kids were like experimenting or fiddling around, and what we decided was sort of appropriate was that if it's undetermined from the computation model as to which process, if the order in which processes are run, and yet the order is going to make a difference in terms of how the system behaves, that to introduce randomness so that you would sort of see visually that you've got a conflict. So if you took a move left behavior and a move right behavior, when this first came up in Playground, you just got one of them because one just happened to be run second and kind of dominated. But afterwards you saw much more of like this indecision in this object. It would kind of go left a few times and then the schedule happened to change and it would go right, you know, and kind of, you saw some sense visually that there was a conflicting kind of behaviors here. So from a computer science point of view, there are these really tricky questions about when there's some order dependency and how to deal with them. And with the behavior composer and in ToonTalk, one of the things that helps is by having sort of a parallel update, so that within each phase of this thing, everybody's reading the same variables and updating what they're going to be on the next cycle. So that means that it doesn't really matter as much what order they're going to run, but you still could get conflicts. And one of the kind of ironic things about all this conflict stuff is that this grew out of work that actually Dean back there who's leaving was part of back at Xerox PARC on concurrent constraint programming languages. And there we didn't have this idea of kind of having them all kind of interacting through this virtual space. Instead they, in ToonTalk terms, there was all communicating and coordinating via birds and nests. And there you really can, you have more control as the programmer as to these issues about the ordering doesn't matter because there's like something equivalent to like message queues. All the birds are being given messages. They're all flying in to the nest. They're getting interleaved. And then some other process is taking them off so that you could avoid many of the kinds of classical problems with concurrency about race conditions and the like, because you've got a different computation model. So that was something I was very excited about with ToonTalk, and it really was important for some projects that kids did, especially when they were exploring the convergence and divergence of infinite sequences of numbers, that those kind of communication ideas that came back to our work on a programming language called Janus. But for the most part, the effort has been ones where you're simulating creatures or little physical entities. And one of the things is because you're doing this sort of time slicing, usually the most common case is that where the order of execution might make a difference at the level of these small kind of approximations or thin slices. So if you're turning and going forward, which one you do first, if it's very small amounts each time, is going to make a very small difference to the behavior. While if it's because you're doing small amounts every 20th of or 50th of a second. So frequently these kinds of ordering constraints were never even noticed or visible. But of course, there's a computer scientist in me says, you know, we should be more, shouldn't be so sloppy or something.
That's all the questions. Thank you very much for
All right, thanks. Sure.